In this video, we will be looking at how to make solutions. So when we think about making solutions, this is one of the most practical skills that we have in chemistry. It's something that's done all the time. And not only is it needing to be done all the time in the laboratory setting, other disciplines make a lot of use out of this as well. Just to name a couple: environmental studies, biology, anything that involves dealing with things in solutions. You really need to understand how to make different solutions. So everything in solutions basically revolves around concentration. When we think about concentration, concentration answers one simple question: how much solute is in the solution? And we have a lot of different ways of describing that. If we go back to something we talked about in a previous presentation about the simplest solution you could think of, kind of making lemonade, dissolving sugar into water. Well, I want you to think back to when you were a little kid. When you were a little kid, did you necessarily follow the instructions on the packet or on the box how to make the lemonade? Maybe. Or maybe you put in a whole lot more sugar than was actually called for in the directions. The difference between adding that whole bunch of more sugar versus following the instructions was a difference in concentration. How much solute was going to end up being in that solution? Now, we can do a little bit better than saying a small amount, the correct amount, a whole lot. We can actually quantify this. So there's many different concentration units, but the one we're going to focus on is going to be molarity. So when we talk about molarity, molarity is moles of solute per liter of solution. It has that capital M for its symbol. Sometimes it's even shorthanded more. Capital M is moles per liter. Moles of solute per liter of solution. And the key thing for making solutions and dealing with solutions of any type is just recognizing that this molarity can be used as a conversion factor. Just like you use any other true statement as a conversion factor, we can now use molarity as a conversion factor. What's molarity going to convert between? Moles and liters. Sometimes you're going to see the moles in the numerator and the liters in the denominator. Sometimes it's going to be switched based upon what you exactly need in order to solve that problem. But now we're going to start using this in conversion problems, in dimensional analysis problems. It's another technique we have to employ in order to solve problems. So let's look at some solution making problems. This first one is a very basic thing that you need to do anytime you're in a laboratory setting. You need a 0.65 molar solution of NaF. If you only had 24.8 grams of NaF, how many milliliters of that solution could you actually make for that? So sometimes for these solution problems, there's a little bit of an issue of where do you start at? You actually have two given pieces of information here. You have both the grams and the molarity. Luckily, there's an easy solution that's also a universal solution to how to deal with this when you have more than one thing to start off a problem. You always start with the more fundamental unit. Start with the more basic unit. So when we look at the units between grams and molarity, remember that the molarity is really moles per liter. Well, it's pretty easy to see that grams is a lot more basic than that. We're going to start with our grams. So we know that molarity is going to be a bridge between moles and liters. Well, milliliters we know we could get from liters. So grams, whenever you're in doubt of where to really start on a chemistry problem, generally getting to moles is not a terrible idea. So that's going to be our first step. We're going to convert grams to moles, just like we've been doing quite a lot of already. 24.8 grams of NaF, use the molar mass of NaF, 1 mole of NaF, 41.99 grams of NaF. Grams of NaF cancel. Now we have moles of NaF. We're trying to get to a volume. That's what the molarity is for. This molarity at the top, this 0.650 molar solution of NaF, that tells you how many moles of NaF it is in 1 liter. So our conversion factor is 0.650 moles of NaF and 1 liter. That's our true statement. Now it's a matter of how do we arrange that to get to where we need to be. Well, I have moles of NaF already in the numerator, so I need to put the moles of the NaF in the denominator and leave the liters in the numerator. So moles of NaF in the numerator are going to cancel with moles of NaF in the denominator. Last step, this problem asks for it in liters, asks for it in milliliters. Right now we're in liters, so we need to do a milliliters to liters conversion. 1 liter, 1,000 milliliters is our conversion, just knowing our metric prefixes again. Liters are going to cancel. The unit we're left with is the unit we want to be left with, which is going to be milliliters. Again, go through the calculation, multiply across the top, 24.8 times 1,000 divided by 41.99 divided by 0.650, and you're going to end up with 909 milliliters. Now, if we go back and kind of look at the general steps that happened in this problem, what you're going to see is there's only one new step. A lot of these things we've already done before. If I look at this first step, going from grams to moles, we've been there, we've done that quite a bit. That's just using the molar mass to interconvert between grams and moles. The very last step we did, liters to milliliters, well, we've been doing that since the very first chapter. That's just being metric fluent and knowing our metric prefixes. The only new step in this problem was using that concentration, going from moles to the liters. And how are we getting from moles to liters or liters to moles? That's where the concentration is coming from, that molarity. That's what we're going to see in a lot of these problems. It's using things that you've already done before and then tacking on molarity to that as a conversion factor. So our next problem, again, another very practical laboratory problem you would find yourself running across a lot. It says, for a large series of tests spanning many weeks, you know you will need 20 liters of 0.3 molar calcium nitrate. Well, you know that's how much you're going to need for this series of tests. How many pounds of calcium nitrate do you need to ensure that you have enough to make the solution? Well, it may seem a little bit strange that we're dealing with pounds instead of metric, but you know, if you had to order this and the company you're ordering from sold it in pounds, you would still need to be able to deal with pounds. So some useful information here, 2.2 pounds, 1 kilogram. Again, we have a choice of where to start from. We have different pieces of information that we could choose to start with. We have liters and we have molarity. Which one are we going to start with? We're going to start with the more fundamental unit. The more fundamental unit with this will be liters. So that's where we want to start the calculation at. So we have 20 liters. We want to get away from liters towards some sort of mass or weight. We know moles can do that. So can we get from liters to moles? Yes. That's what the molarity is doing for us. That 0.300 molar at the top, what is that telling us? That's telling us how many moles of calcium nitrate we need per liter. We're just going to use that as a conversion factor. I want the liters to go away, so numerator and denominator. I'm going to leave the moles in the numerator, so my liters will cancel. Now I have moles. At this stage, this is really not even a solution problem anymore. We dealt with the solution. This now just uses things that we've previously learned in earlier chapters. Mole to gram conversion using the molar mass. You tally up the molar mass for calcium nitrate. It's 164.1. We want the moles to cancel, so we put the moles in the denominator. Now we're at grams. Ultimately, we wanted to go to pounds, and our conversion factor had kilograms and pounds as a way of interrelating those. So a quick gram to kilogram conversion. grams in the numerator are going to cancel with the grams in the denominator. Now I have kilograms. Now I can use that metric to English conversion to get to the unit I needed, which was pounds. So kilograms in the numerator, kilograms in the denominator. What I'm going to be left with is pounds of calcium nitrate, which is what I wanted. So if you go through and do the calculation, multiply across top 20 times 0.3 times 164 times 2.2, and then divided by 1,000 in the denominator, and what you're going to get in that is your 2.17 pounds that you need in order to make this solution. If we review the steps again, we're going to see there's only one new step. The new step I'll put here in purple. It was the very first step in this case. It was using that molarity. Molarity is a bridge between moles and liters, and that's how we did it. 20 liters, moles and liters using that molarity. All the other steps, I'll put these in green, been there, done that. Moles and grams, been there, done that. Grams and kilograms, been there, done that. Kilograms and pounds, been there, done that. The new step was the very first step in this, going from our liters to moles using that molarity as a conversion factor. So another problem that we can do that involves solution making is if you took 17.5 grams of magnesium bromide and you dissolve it in enough water to make a 68.4 milliliter solution. You just want to know what's the molarity of the solution. Well, for the molarity of the solution, molarity is always moles of solute per liter of solution. Well, let's just get the moles and get the liters. It's just a couple of one-step conversions, then putting it together. The information is given to us in grams, so 17.5 grams. We just need to do a one-step conversion using the molar mass in order to get those grams into moles. And again, grams in the numerator divided by grams in the denominator. What we're going to be left with is moles. So you do that one-step conversion that you've been doing a lot of already. So when you go through that one-step conversion, you're going to get your 0.0951 moles of magnesium bromide. Well, that's the mole part in the numerator. Now we just need to deal with the volume part in the denominator. Well, I need it in liters. Right now I'm in milliliters. Well, that's just a one-step conversion. Milliliters to liters conversion, something we've seen a lot of. Milliliters in numerator, milliliters in denominator are going to cancel. What will we be left with? We're going to be left with 0.684 liters. Now we have the numerator, we have the denominator. We just need to do that final calculation. 0.0951 moles of magnesium bromide in the numerator, 0.0684 liters in the denominator. We do that division, we'll get 1.39 as our molarity of the magnesium bromide. So again, a lot of this solution making uses some of the things we've done previously and then just tacking on what the molarity means, moles per liter. So the one kind of new type of thing in order to get a grasp of, in order to make solutions, is to do it as a dilution. When we're doing a dilution, what we're doing is we're making a less concentrated solution starting from a more concentrated solution. Sometimes that's called a stock solution, that more concentrated solution. You often want to do it this way because it's often easier and quicker to do a dilution in order to make a solution than starting from just the solvent and then the liquid solute. This is extremely useful when your solute is a gas. It's a real pain. It's really challenging to try to weigh out and measure out and manipulate a gas. So if you can already get something that's dissolved in there, then the dilution may be much quicker and easier way of making these solutions. So we want to be able to deal with solutions, making solutions from doing a dilution. So I want to draw a very quick and crude picture of what's happening with the dilution, because if you can follow what's happening with this picture, all of the calculations and the math that go along with doing a dilution become a lot more clear. So when you're diluting something, you're taking a concentrated solution. That's what you see on the left. The red X's represent the solute particles. I have a concentrated solution. Well, if you want to make a more dilute solution, you're going to add solvent to that in order to dilute that. That's what the second kind of picture is. Kind of in the middle diagram is just showing us adding solvent. Then at the end, the right-hand picture shows the result of that. So it kind of shows you what's happening. You can definitely tell that we ended with a less concentrated solution than we started with. So there's a couple things to notice in this picture, and then we're going to put it kind of in more of a mathematical equation. The amount of solute in the diluted solution is the same as the moles of the solute in the concentrated solution. We can see that in the picture. If you look at the concentrated solution on the left, you see 1, 2, 3, 4, 5, 6 solute particles. Well, how many solute particles do you see in the diluted solution on the right? 1, 2, 3, 4, 5, 6. The moles of solute didn't change in this. Why? Because our solvent that we added didn't have any solute in it as part of doing a dilution. So that's the first thing you want to notice in this diagram. Second thing you want to notice is that the volume of the concentrated solution plus the volume of the diluted, the volume of the concentrated solution plus the volume of the solvent will equal the volume of the diluted solution. We kind of look at this and we say, okay, where's our volume at? We have that much. We have that much. How much volume will we end with? Well, combine those two volumes. So these two things that you can kind of easily see in the diagram, we're now going to use this to actually solve quantitatively some problems. So when we're looking at a dilution, there's an equation that gets used for dilutions. It's called M1V1 equals M2V2. And what each side of the equation represents is either the concentrated or the diluted solution. Doesn't matter which one you put on each side. And here's why this equation works great for dilutions. If I list the units that each thing has, molarity is moles per liter. Volume is liters. If I do the same thing on the right-hand side, molarity is moles per liter. Volume is liters. So I'm looking at this equation, and you'll notice that the liters cancel out. If the liters cancel out, what are you left with? Moles equal moles. Think back to that picture we just did. We said the moles of the solute were the same. Well, that's why this equation works, is because you're basically saying I have equal number of moles on each side. So our moles are equal, and the volume ends up canceling out. So a little bit of a word of warning here. This equation, M1V1 equals M2V2, should only be used for dilution problems. Sometimes what ends up happening is people like this equation. It's pretty straightforward. It's pretty simple. They can do the calculation. They start using it anytime they see a problem. It doesn't work for other types of problems. Don't use it for any problem that's not a dilution. And here's why. For most other problems, this fact of moles equaling moles is not going to be true, which means this is not going to work. So only be using this equation when you're doing a dilution problem. Let's actually look at a specific dilution problem. So this problem says, describe in detail how you would prepare 575 milliliters of 0.340 molar KBr from a stock solution that was 12.2 molar. Well, first, how do you recognize that you're dealing with a dilution? Well, you're asked to make a dilute solution 0.340 molar from a more concentrated solution. Well, that's the very definition of doing a dilution. So if we're going to do a dilution, we're going to use M1V1 equals M2V2. That's got to be used here. Doesn't matter which side you make the diluted solution, which side you make the stock solution. I made the left-hand side the diluted solution, so I'm just filling in information. The molarity of that diluted solution, 0.340 molar. The volume of the diluted solution, 575 milliliters. Now you may be looking at this and saying, boy, I really thought we needed to convert that to liters in order for everything to cancel. Well, you can convert it to liters. That would be fine. There'd be nothing wrong with that, but you don't necessarily have to. Remember that our volumes are going to cancel out. So if your volumes are ultimately going to cancel out, what you can do is you can save yourself a little bit of work. You don't have to convert this to liters. You can leave it in milliliters. The thing is, if you leave it in milliliters, what happens is that just makes the other volume that you're solving for also come out in milliliters, and that's fine for that. So I left it in milliliters. The right-hand side, the stock solution, the concentrated solution, that's 12.2 molar. And what we don't know, what we're trying to solve for, is what is that volume of that stock solution? How much of it do we need to use? So in order to solve this, you have to do a little bit of algebra, isolate the variable, the volume of that stock solution. So in order to solve this, you would multiply the left-hand side, 0.340 molar, times the 575 milliliters, and then you would divide by the 12.2 molar. That would isolate your volume of your stock solution. When you do that, you'd find it'd be 16 milliliters. Well, what does that 16 milliliters represent? That 16 milliliters represents the volume of that stock solution. That's how much of that 12.2 molar solution you had to start with. Now that doesn't fully answer the question though yet. The question says, or the problem says, describe in detail. Well, there's still another part. Whenever you would do a dilution, it's always the combination of some amount of a stock solution with some amount of the solvent. In this case, our solvent would be water. Well, how do we figure out how much water we need? Well, here we kind of use the idea that the volume of that final diluted solution is additive of the different things that went in to create it. What did we already find? The total volume of that solution is 575 milliliters. Well, 16 milliliters of that is our stock solution that we just calculated from M1V1 equals M2V2. So where does the rest of it come from? So just do a subtraction. 575 minus 16 would be 559 milliliters. Well, what does that represent? That's how much of your solvent you would have to add. In this case, our solvent is water. So in order to really make the solution, here is what you would have to combine. You would have to take 16 milliliters of your 12.2 molar KBr and combine that with 559 milliliters of water. So those two things that you would have to combine. You always have to describe how much of each thing, how much of your stock solution and how much of your solvent you need in order to make that solution. And the volume of the stock solution, that's what's coming from M1V1 equals M2V2. And then you're getting the volume of the solvent based upon kind of the difference between the total and what you've already used. Again, this solution making is very, very practical skill. You run across this all the time when you are in laboratory settings.